Hello and welcome. My name is Dr. Mark Taylor, and this is the first of a series of videos reviewing the Delaware Tech Physics 111 Exam 1 Preparation and Practice Exam covering motion, also known as kinematics. At this point, I'm going to pause the video and we'll switch over to the practice exam itself. Okay, so looking at the practice exam itself, you see there are a number of topics, definitions of scientific terms, followed by definitions of scalars versus vectors. Then we'll talk about the various kinematic terms. These are various properties along with units for those and if there are any formulas. These include distance versus displacement, speed versus velocity, and acceleration. And then we'll move to graphing some of these pieces of information in order to gain knowledge about other pieces of information related to kinematics. And we'll be doing different kinds of graphs. We'll be doing position versus time graphs, also known as x versus t. And we'll be doing velocity versus time graphs, also known as v versus t. In each case, we'll be plotting the graphs and analyzing them. Then we'll be taking the slopes at various parts of the graph in order to get new pieces of information. And then in the case of velocity curves, we'll also be calculating areas between the graph itself and the x-axis to determine displacement. Then we'll spend just a little bit of time doing metric conversions. These are conversions between different metric units. For instance, going from meters to kilometers or kilometers to meters, etc. And then we'll talk about the equations involved in solving kinematic problems. There are some very simple equations used when the acceleration is zero. We usually use what we refer to as the speed equation or velocity equation. And then we'll talk about using the series of 5 kinematic equations to solve both horizontal motion and vertical motion problems. In the case of vertical motion, these are problems where the acceleration is strictly due to gravity, also known as the g, lowercase g, meaning the acceleration due to gravity. We'll talk about a strategy for how to solve kinematic problems, and then we'll actually be doing these kinematic problems. And then there's an answer key that you can always refer to at the end of this. All right. So let's start with these scientific terms. And there are 4 scientific terms you're responsible for. Scientific hypothesis, scientific theory, scientific law, and scientific fact. And in each case, we have the term, the definition, an example, and a brief statement over whether it can change over time. This is really for your additional education. You won't be responsible for that last column. So the 2 most important terms for you to understand in any introductory science course are hypothesis and theory. And we are specifically talking about scientific hypothesis and scientific theory. And these 2 words are not used the same way as in everyday English. In everyday English, we tend to use hypothesis and theory to mean the same thing, but in sciences, they have extremely different definitions. A hypothesis is your good educated guess at the beginning before you've done any real experiments to test it. In other words, you've observed some phenomena and you think about it a little bit, and you think, okay, what might be the explanation for this? What might be happening? And that's your hypothesis. It's a good educated guess. But to be a scientific hypothesis, it also has to be what we refer to as testable and falsifiable. Testable means we have to be able to come up with experiments to test whether the hypothesis is correct or not. And falsifiable means that experiment or those experiments we do, they have to have different possible outcomes from the experiment. Before you've even done the experiment, you have to think about what the experiment might result in, what are the possible outcomes, and at least one of those possible outcomes must be a result that tells you my hypothesis is just wrong. It's either wrong a little bit or it's wrong a lot, and we have to replace it with a new hypothesis. So it has to be what we call falsifiable, meaning at least one possible outcome says the hypothesis is just wrong and you need to start over again. All right. So an example of a hypothesis would be plants grow faster under blue light than red light. And you can imagine growing plants under blue light and plants under red light. And if the plants grow faster under red light, well, you know the hypothesis is wrong. But if they grow faster under blue light, your hypothesis might be right, but it might not be the real explanation. Maybe you're using blue light that happens to be more intense and the plants like more intense light. Or maybe the red light you're using is hotter than the blue light and it's damaging the plants or it's making the water evaporate. So you tend to get two types of possible results from your experiments. One set of outcomes that say your hypothesis is wrong, come up with a new one, or your hypothesis might be right, you need to come up with more tests to be more sure. And you really can never be 100% sure. You can be very, very, very sure after you do enough experiments. But once you've done enough experiments where you are really quite certain that your hypothesis is the best explanation of what's going on, we no longer call it a hypothesis. We elevate it to the term theory, specifically scientific theory. So now a theory is well substantiated and a comprehensive explanation. And that means that you've tested it over and over and over again, and it still holds up. No one well-performed experiment said your idea was wrong. Everything says it might be right. And it's almost impossible to come up with experiments that say you're absolutely right. You're constantly narrowing it down to what you think is the correct explanation. And so it's supported by a large body of evidence, meaning you've done many different kinds of experiments. You've done them over and over again. You're not the only one doing them. Other people are doing them. And now it's the best explanation of what's happening. And that is a scientific theory. And that's the way scientists use the word theory. So the theory of natural selection to explain evolution, atomic theory to explain the structure of the atom and the behavior of the atom, and the theory of general relativity. This is a theory come up with by Einstein in 1915 to explain how gravity works. Newton figured out what gravity does. Einstein figured out why it works. And that's way beyond the scope of this course, and I'd be happy to explain it offline. But these are examples of a theory. And then we have two other terms, law and fact, scientific law and scientifically observable fact. So a law is a general descriptive statement. It's usually in a mathematical form. It doesn't always tell you why something's happening. It tells you mathematically what we observe, or it doesn't have to necessarily be mathematical, but it tells you what we observe, and it gives you a framework for what to expect when you're looking at different aspects of nature. And examples of scientific laws would be Newton's 3 laws of motion, which you'll learn about in the next unit. Newton's universal law of gravitation, which is the formula that predicts how strong the gravitational force is depending on the size of two masses that are interacting and the distance between those masses. And then Coulomb's law was another law that relates to the attractive or repulsive force between two electric charges, a positive and a positive, negative and a negative, a positive and negative. And Coulomb's law predicts the strength of that quite well. And then a scientific fact, this is just something you observe, and you always observe it if it's done under the same conditions every time. It's repeatable, it's confirmed, and you can always measure it and you get the same results every time. So an example of that would be water boils at 100 degrees centigrade at sea level at 1 atmosphere pressure. In other words, if you set the temperature at this and you set the atmospheric pressure at a certain amount, you will always see that water boils at that temperature under those conditions. So that's a fairly stable observation, and it will be the same observation no matter who does it, as long as they do it under those conditions. And with this, we'll stop and we'll go to the next section in the next video.